All right, welcome. Last chapter on nuclear chemistry. Nuclear chemistry, pretty much in chemistry, we talk about electrons and how electrons interact. Nuclear chemistry, it's all about the nucleus. And the general idea here is that nucleus of an atom, you have a really tiny area with a bunch of positive charges. And you have those positive charges are repelling. They want to blow the nucleus apart. So there's a stronger force known as the nuclear strong force that holds the nucleus together. So the protons and neutrons, they both exhibit the nuclear strong force, and that's what binds the nucleus of an atom together. And if the nucleus is unstable, so if there's not enough strength in the nuclear strong force to hold the nucleus together, the unstable nuclei, we refer to those as radioactive. So originally radioactive meant they released radio waves, or they even said uranic waves, so the uranium. It turns out it's more than just radio waves. It's it's gamma rays, it's a bunch of other stuff. So it's, if you wonder where the term radioactive came from, is from that. But they're essentially it's unstable. It's unstable, and we'll talk about where things are stable and things are unstable. And also, any element heavier than lead or bismuth, bismuth is debatable whether or not it's stable or not, is radioactive. And what we learned all about electrons, about the s orbital, p orbital, d orbital, that kind of thing, that's the same for protons and neutrons. They have s, p, d, e, f, g, h, i, all those different types of orbitals. The difference is, so energy levels, they can either be degenerate or maybe they're just slightly different. Nuclear energy, they're huge. Huge energy differences, and they don't interact. So actually, nuclear chemistry, nuclear physics is pretty easy because the math is easier because these energy levels are so vastly different, they don't interfere. Electron energy levels, electrons act like waves, and they all interfere with each other, and they have these crazy wave patterns, and if you're trying to do the spectroscopy on that, it's really, really difficult. Or if you're doing the calculations, it's really difficult. Nuclear, they don't interact. There's just huge energy levels. It's just doing some basic principles and then doing that. So actually, nuclear chemistry later on, if you go and study it in grad school, it's really easy. I studied it for a little bit. And for nuclear equations, so nuclear equations it's also easier than traditional chemistry. The top numbers and the bottom numbers must be equal. So the top numbers are the mass numbers. So the mass numbers are the numbers of protons plus the number of neutrons. The bottom number is the atomic number. That's the number of protons. That's also the number of charges. So the top number is the total number of protons and neutrons. The bottom number is the total number of charges. So let's start off by talking about the different types of decay routes. And so I'm using the Greek letters alpha, beta, gamma. So alpha decay. So alpha decay here, we have uranium-238, uranium-92. So this is the parent nucleotide, and this is going to decay down to thorium. Thorium, this is known as the daughter nucleide. Sorry, this is the daughter nucleide. So we only have daughters. Okay, so elements can only have daughters. And alpha decay, the alpha particle is a helium nucleus. And then also, whenever there's a nuclear transition, a gamma ray is produced. And that's a photon. That's a very high energy photon. And these high energy photons are easy to detect. It's really easy to know the concentration of anything that's radioactive. You just use a Geiger counter, you can figure it out. It's very, very quick. But if you notice something, so uranium, the top, 238 on the top, this equals 234 and thorium plus 4. So 234 plus 4 is 238, so the top numbers equilibrate. The gamma ray is a photon, it has no charge and also has no mass. So then the bottom 92 protons is 90 protons in thorium and 2 in helium, so 90 plus 2 is in fact 92, and 0 doesn't matter, right? So the top numbers and the bottom numbers equilibrate. So, and an alpha particle, you can block this with a skin or a sheet of paper. It's not that hard. I can, they're really heavy, but they're really easy to block. Now, alpha particles, though, they're easy. If they're outside your body, they're not very difficult. They're not dangerous. Alpha particles inside your body, though, it's like a pinball, if you've seen an old pinball machine. So radon, for instance, alpha decays. And if you breathe in radon and then it alpha decays inside of your lungs, it'll be like a pinball machine yelling beep, 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 all inside your lung, and it can cause massive amounts of damage. And that's one thing with radiation. So the radiation, the gamma rays, and like the alpha particles, like what danger is there in radiation? It just breaks chemical bonds. It's dangerous because it destroys things. And we'll talk about radiation effects later, but it just basically causes cellular damage. It can cause cancer if there is damage to the DNA and it's repaired incorrectly. But most of all, people that get injured from radiation, it just hurts. So a sunburn is a radiation burn. It just hurts. So same thing with this. Okay, so alpha decay. And alpha decay will decrease the mass by 4, decrease the atomic number by 2. Then there's beta decay. Beta decay is when a neutron, and this isn't any element, and a neutron, it can be a free neutron's beta decay. A free neutron will turn into a proton and an electron. And the electron is the beta particle. Beta particle have a little bit stronger penetrating power. They can be blocked by a thin sheet of metal or or a block of wood. So like a frying pan could block beta particles. So or a piece of wood, like one of the planks of wood that my colleagues like to break in Taekwondo, or I guess it's judo. I don't know. They go on the Great Lawn and they break pieces of wood with them and their students. So that one of those that would block a beta particle. So also plastic. Plastic is actually a really good blocker of beta particles. So if you wear your plastic safety glasses, that'll stop beta particles as well. So, but notice again the top numbers. So 1 neutron is 1 proton plus 0 electron on the top. So 1 equals 1. And 0 on the bottom, 0 equals 1 on the proton and minus 1 on the electron, so 0 on the bottom. So that's still the top and the bottom are blocked. So alpha particles you can block with a piece of paper, beta particle, block of wood. A gamma particle, you need feet of lead or meters of concrete. So like 10 feet of concrete will probably block it. Or like a foot or so of lead. Depends on how many particles are coming off. I mean, like if it's something that's a really high amount of radiation, like a particle accelerator, you need some real thick pieces of lead. But if it's not something kind of mild, like a nuclear power plant, they usually use concrete, and about 10 feet of concrete will do it. I mean, it's still a lot of concrete, but it's nuclear power plant it's not too radioactive, at least in proper operations. Of course, if it explodes, that's a different story. Okay, so going on, talking about different types of decay, there's positron emission. And if you've ever heard of a PET scan for the brain function, that uses positron emission topography. That's the PET. And a proton can turn into a neutron and a positron. So the positron, this is the electron with a +1 charge. That's antimatter. And matter and antimatter combine to form gamma rays. So the positron, you're producing positrons, and then that'll react with an electron, and the detector is detecting the gamma rays. Electron capture, sometimes referred to as K capture. K capture is the German for Kern for first. So the first capture, electron capture, it's in the 1s orbital is where the electron captures. The proton will absorb an electron and turn into a neutron. So, and if you look at this chart, this is the modes of radioactive decay. Here's the prettier pictures than my things. You have a parent nuclide and then the daughter nuclide, and it releases a alpha particle. And here's beta decay. A neutron in the parent nuclide turns into a daughter nuclide. What happens in a beta decay is the atomic number increases by 1. The mass stays about the same. Well, essentially, we consider it doesn't change. It loses it like electron plus energy, but The atomic number increases by 1, then the total mass number stays the same. Excited nuclei X, this is anytime there's a nuclear transition, there's a gamma ray, basically. So positron emission, we lose a charge by -1. Same thing with electron capture. The proton becomes a neutron. So both positron emission, electron capture, the nucleus stays the same mass more or less, and the charge changed by a factor of -1. Now I told you about the nuclear stability. If you look at these here, the value of stability is here, and it starts off with the charge per mass ratio being 1. So this is the number of protons and number of neutrons are the same. So it starts off kind of that way, but you notice then the graph kind of goes up this way. So why do we have that shift? It's because the neutrons exhibit the strong force, and as the nucleus becomes more and more positive, it needs more and more of that nuclear strong force to keep the thing bound together. And also, with stability, the even numbers tend to be much more stable. It's very rare that you have an odd number of protons and an odd number of neutrons. There's very few stable nucleides with that. Usually you have an even number, and that's something called the pairing energy. So when you have an energy level, the proton and a neutron, if they're same as electrons, they have spin up and spin down. If they're paired up, this just releases something called the pairing energy, and that makes it especially stable. That's also so the nuclear fuel that we use, the uranium-235 and plutonium-239, we use those in nuclear reactors and nuclear bombs. They're the odd number because when it releases the pairing energy, that causes an excitation in the nucleus and can cause fission. So, okay, so the magic numbers, there's magic number in stability, there's magic numbers for electrons. It's 2, 10, 18, and so on. Those are the numbers of electrons in the noble gases. Same thing with nuclear chemistry. 2, 8, 20, 28, 50, 82, and 126. These are the magic numbers. These are especially stable configurations. And of particular interest is 28. So iron 56 is the most stable element, nuclear-wise. So we'll talk about that soon. Let's talk about how we detect radiation. So film badge. This was erroneously said as a radiation shield. Have you ever seen James Bond Goldfinger? They say radiation shield. It's a dosimeter. It's not the radiation shield. They just see how much a person's dose is. They're film badges, and then every once in a while you take them and they check your dosage. And it's the things you wear here on your shirt, or sometimes you wear it on your belt. You can also wear them as rings. So we'll talk about radiation dosage later, but a person is allowed to get 5 rem of radiation. You don't start seeing physical effects till about 20 rem. If you are government certified, which means you take a course, it means you can get 10 rem. And your hands can get a higher dosage because your hands are not necessary, whereas like your head and torso are. So they allow more dosage to someone's hands. So if someone is working with his or her hands, they give them rings to measure the dosage of that as well. Geiger counter, also known as a Geiger-Muller counter. Here's an image of that. You have a tube that has argon gas in it, and then as the ionizing radiation goes through, it ionizes the argon atoms, and then the signal gets sent through a detector, and then it can either just be a number, or maybe you're familiar with the clicks, the click, 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 click of the Geiger counter, and it's really good at measuring gamma rays, especially. Then there's a scintillation measurement. This is sodium iodide or cesium iodide. When it's struck by a high energy particle, it makes a flash of light. and you can detect the light. So those are the ways that we can detect radiation. So I mentioned nuclear power plants and how nuclear reaction works, and I told you already about the Perryin energy. So the odd number of neutrons there, uranium-235. So the odd number are the fuel for this. So uranium-235 will absorb a neutron, release the Perryin energy, and then it creates an excited nucleus. And the excited nucleus, if it wants to, well, it depends. There's a couple ways it can decay down. A relatively uncommon way is to undergo nuclear fission. And here, there's other products other than barium and krypton. There's several different types of products, but it can decay down into that, and then that generates more neutrons, and then these neutrons can be absorbed by other nuclei, and then this is known as a nuclear chain reaction. So a couple of things about these neutrons. These are known as thermal neutrons, which means they move relatively slowly. There's fast neutrons. Fast neutrons tend not to be absorbed. Fast neutrons can be used to fizz things, but it's usually rare that event happens. That does happen in some types of nuclear weapons. So a neutron bomb has fast neutrons coming out of it, and that can be used to increase the yield. If you coat the outside with depleted uranium, for instance, that'll give you a stronger yield. But you can take fast neutrons, you can slow them down with a moderator. Water is a very common moderator. So that's also why nuclear power plants are in water. There's different types of moderators. There's liquid sodium is another one. Liquid graphite has been used. That was used in a Chernobyl explosion. That's that reactor ran off of liquid graphite. It's tend not to be used outside of the Soviet Union, and even then they tend not to use them. We typically, in the United States, we usually use water. And in Canada, they use heavy water. Most places, we use water. So here's a nuclear reactor. And so we do here in the United States is we typically enrich uranium to around 3%, maybe as high as 9%. So we take the uranium from the ground is typically about 0.7% uranium-235, and we react the uranium with fluorine to make uranium hexafluoride, and then we can run that through a series of centrifuges to enrich the uranium, and we enrich it to 3% or like less than 10%. And in Canada, they use heavy water reactors. They just put the uranium straight from the ground into the reactor. So, but we prefer to use light water or regular water reactors at a nuclear power plant. But the way this works is that you have the reactor core right here, and you have the pile. The pile is literally a pile of uranium oxide, and they're usually in about like a hockey puck kind of thing. They put a pile on them, and in between them you have control rods. And what the control rods do is they absorb neutrons. And then when you bring the control rods up, the nuclear reactor is on full power. If you put the control rods down, you say the nuclear reactor is off. There's a couple of terms about the nuclear reactor came from the original one in Fermilab. I saw a picture of it. It's pretty funny. The pile is literally a pile of uranium oxide, and the control rods are like 2x4s with beryllium, like taped to it with athletic tape. And there's a guy sitting there with an axe, and there's above the reactor is this series of control rods suspended to the ceiling over a pulley with a rope, and the guy is sitting there with an axe, saying if they say axe it, he hits the rope with the axe and the control rods fall down. So they use that terminology in power plants. The pile is the reactor core, and then the axe is when the control rods fall down. That's the fail safe. So we tend not to run the nuclear power plants very hot, so on the order of 500 degrees Celsius. So a candle flame is 550 to 600 Celsius. So a candle is hotter than a nuclear reactor in terms of temperature-wise, but it has a lot of energy in it. So then we have thing with the United States. We don't have a set design for our nuclear reactors. This is one of them. So we can. This is a pressurized water reactor. the nuclear reactor heats up water, and then that water heats up steam, and then that steam goes and turns a turbine. And typically, it uses saturated steam, doesn't use superheated steam for this, so it's a little inefficient that way. So a nuclear power plant is usually about 20% thermally efficient. That's about the same as a car engine. A coal burning plant is about 33% efficient. So, but they use superheated steam for that. But okay, so that's a nuclear power plant, and the advantage of a nuclear power plant is that it just has so much energy density. Okay, so let's talk about something else. If you look at this graph here on the left, you have binding energy per nucleon, and on the x-axis you have the mass number. And notice something, that there is a peak, and that's at iron 56. And so this is important because nuclear fusion up into iron 56 is exothermic. It releases energy. And nuclear fusion after iron is endothermic. It absorbs energy. And this is the cause, among other things, for a phenomenon known as a type 2a supernova. So what happens in the type 2a supernova is a star with 3 solar masses or above that can eventually it can start to fuse iron. So our sun is not going to type 2a supernova. What's going to happen to our sun is that it's going to burn up all of its hydrogen to form helium, and then helium is going to burn to form carbon, and then the sun will get too hot and it'll expand and turn into a planetary nebula. So we will not type 2a supernova, but a star big enough, around 3 solar masses or greater, could do this. So it will eventually start fusing. It'll fusing things into iron, and after a certain point in time, enough iron will build up in the core of the star, and then the star will start to fuse iron. The problem with fusing iron is it's endothermic, and you know from gas laws, when you cool a gas, the gas shrinks. So the core of the star will shrink rapidly, and it'll implode, and the implosion will cause a shock wave, an explosion, and the star will nova. And also during the nova stage, the star will have a tremendous amount of nuclear fusion and generate, and this is how many of the elements heavier than iron are produced, are in the nova stars. Now we have some of that stardust with us. So among other things, we have uranium. And you can see uranium, though. Uranium is exothermic upon fission. So fission is breaking apart nuclei. Fusion is bringing it together. It's like a bone fusion. You take 2 bones and you fuse them together into one. A fission is when you break things apart. So uranium fission is exothermic, and we get lots of energy from that. But look at this. Here is the fission from that. There's this about half of one of these lines on the graph. If you compare that to deuterium here to helium, there's much, much more energy available in fusion. So fusion is a much higher energetic process. And that's where stars get their energy. Stars get their energy via nuclear fusion. We do not have proven fusion technology yet, or at least controlled. So we can make nuclear fusion. We can do that in certain types of nuclear weapons. And we have 2 machines that can do it. One is called a tokamak. That's kind of a donut-shaped thing where you have a plasma, and you can high energy plasma and slam it together. You can get fusion, but we haven't made an energy positive yet. We put more energy in than we get out. And there's a National Ignition Facility in Livermore. They're doing research on nuclear fusion. We can generate fusion that way. We've got it to work. But the conditions there are kind of exotic. We have a bunch of lasers that we shine down into a small, like Tylenol-sized pill piece, and we've gotten that to compress down enough that a nuclear fusion could happen. So, iron 56. That's important for, like I said, for stars. Okay, so. Last few topics. So where do we get radiation? So this is the United States of America. And so where do we get our radiation? So a lot of people discount this, but the sun is a source of radiation, and the atmosphere shields us from radiation. So if we take a plane ride, so I mean, if you look at a dental X-ray is 30 millirem. So taking, let's see here, so 12 5-hour jet rides, that's the same as dental X-ray. So that's one thing about pilots and flight attendants. They get a healthy dose of radiation, and they get it from the sun. Now, this, of course, is only if you fly during the daytime. At night, there is some radiation, but it's from cosmic rays, but it's not as much. So there's cosmic radiation right below that, and terrestrial radiation. So the Earth has some because we have carbon-14, and in our own bodies as well. I guess also it's already in the body, and outside the body, and there's just the uranium thorium cycle of the ground. And radon there. It also depends on where you live. So here in Hawaii, we essentially don't have any radon, so we do not have that background at all. So that 200 millirem is already out. So diagnostic medical procedures, so chest x-rays, dental x-rays. It depends on what we're getting done. Mammogram, that's I don't have to worry about that personally, but that's a healthy dose. So if you get a CT scan, I've done that. I've done the CT scan. I got a 400 millirem dose of that. So CT scans use that, and various other types of scans. So building materials. So this is because we get stuff like granite, for instance, is going to have a little bit of uranium and in it. So if you're around a lot of rocks, you're going to get a small dose. But this is a small dose. It's not really going to hurt you over time. Luminous watches. And here's a big one, tobacco products. So if you are smoking a pack a day, you're hitting yourself with a healthy dose of radiation there. So 16 rem. So I keep on using the word rem. So rem stands for Roentgen Equivalent Man. And so you're allowed to have 5 rem per year, so about 20 rem you start to feel something. Your white blood cell count gets affected, and you usually don't see any sort of effects for radiation sickness. You might see it as early as 60 rem. Some people lose their hair at 60 rem. So it depends on the person, really. But for 100 to 400, typically 100, you get radiation sickness. And radiation sickness, this is just like having a bad case of the flu. It just makes you feel terrible. I've never had it, but it just doesn't feel good. You've been beaten up on the atomic and molecular level by radiation, and there's this cell damage. Some cells die, some cells need to be repaired, some cells are being repaired, but you feel terrible. So, like I said, it hasn't happened to me. And then it depends, then the rest of the dose depends on how much of a dose you get, and also depends on what type of medical care you have. Problem with the really high levels of doses of radiation, it usually affects your central nervous system, so you don't really quite understand what's going on. So I probably shouldn't talk about how to make nuclear weapons on YouTube. If you really want to know how to make nuclear weapons, I can come to my office hours. I'll tell you all about it. It's not classified, but I also don't have classified. I don't have any type of clearance, so I can tell you how to make them. But I probably shouldn't talk about it on YouTube, just in case Uncle Sam is watching. So let me recap the important things. Know the sources of radiation. Also know the penetrating power. And also how to do nuclear equations. Nuclear equations, the top numbers and the bottom numbers need to be the same. Okay, so that's how you balance nuclear equations. And then the penetrating powers, so alpha decay does not penetrate very far at all. Beta decay has a moderate penetration power. Gamma rays have a very high penetrating power. Inside the body, alpha sources are very dangerous. Outside the body, they're not really dangerous at all. Beta, they're dangerous in both outside and inside the body. So, but all right then. Well, that's it for nuclear chemistry. If you, I entered grad school as a nuclear scientist. I changed to chemistry, but I have a great interest in this. So if you have any curiosity in this, please let me know, and I'd be happy to enlighten you.